In the previous two examples, we looked at using a simple first order filter in order to make a low pass filter and a high pass filter. And looking at the Bode diagrams, they were effective, at least in the input that we gave it, of attenuating what we wanted to attenuate and preserving what we wanted to preserve. But an issue with both of them, it didn't really come up in the examples, but a general issue is that roll-off around the cutoff frequency where we might be attenuating things we want to keep and not attenuating enough some of the frequencies we want to remove from our signal. So one option we have is, well, we don't have to use a first order filter, we can use a higher order filter, and there's different ways we could accomplish this. One thing we could basically do is we can filter it through our first order filter, we can get our output, and we can use that output as the input in another first order filter. So basically filtering it multiple times through the same filter. And that's what we're going to look at in this example. We can also chain together filters in other ways. We can make a band pass filter by putting a low pass filter and giving its output into a high pass filter, or vice versa. And we can make other interesting combinations, and we'll discuss other types of filters at the end of this example as well. So let's look at here, first looking at a second order low pass filter. We'll have the same cutoff as we had previously, and we'll have the same input as we had before. Again, the idea here is that we can make a second order filter by basically passing it through a first order filter to first order filters. So if we look at what the transfer function looks like here, we're taking that low pass filter with the 1 over s over omega c plus 1, and remember that putting a function through two, or a signal through two transfer functions in series, all we are doing is effectively multiplying the transfer functions together. So that's what we can do here to make our second order filter, is multiply two first order filters together. So we wanted to see, what is this going to look like with a 5 Hz cutoff? What's the Bode diagram going to look like? What's the simulation going to look like? Actually, we'll just for comparison look at what if it only went through the one first order filter, and then also what if we put it through 3 of these first order filters, making a third order filter? How's that going to affect it? And then finally, again, how can we construct a second or a third order filter in general? In the MATLAB, we're going to see, again, the same cutoff frequency, and I'm going to make this RF1 the same way I did in the first example. So I'm making that transfer function with the 1, and then the 1 over omega c times s, and then a 1. So let me just do that part so far so we can see what that looks like. And that's my RF1. And I can see its Bode diagram, and what I'm going to do is make 2 more Bode diagrams. I'll put them all on top of each other though. So the second one we see in line 302 here, this is going to be the second order filter. So yeah, second order filter, I can just chain together 2 of these first order filters and multiply their transfer functions together. So I just have RF1, I'm going to square it. I'm going to multiply it by itself. And now I'll make a third order filter by chaining together 3 of these, and that's the RF1 cubed. And we'll see how that affects it. And we'll see all 3 Bode diagrams on that same plot. All right, so enlarging it here, we can immediately see some differences. So the blue is that first order filter, exactly that we saw in that first example. The orange is the second order filter, and the yellow is going to be this third order filter. So what we can see in the Bode diagrams is that the roll-off has certainly changed in all 3 of these filters. All right, so the blue one we see on top is slower to attenuate. The magnitude goes down slower at those higher frequencies. It goes down faster for the second order and faster still for the third order system. So on the plus side, it's going to more quickly get rid of those high frequency signals, and that's what we want our low pass filter to do. So as we increase the order, it more harshly is going to remove those high frequency signals. So that's good, that's on the plus side. On the minus side, we see with these passive filters, as we increase the order, the phase is getting more and more affected. It's getting further and further to 0 as we increase the order. And typically this is then kind of on the downside, we don't want this to happen. We're delaying further and further what our output looks like compared to the input. So it's relatively closer to zero for the first order system as we get closer and closer to that cutoff frequency, but then the phase increases more and more as we increase the order. And if we looked at a fourth order or a fifth order, we're going to see this trend continue. So the phase is getting worse, even though the roll-off in the magnitude is getting better. It's more like what we want to be getting rid of those higher frequency signals faster. So based on looking at the Bode diagram for this low-pass filter, looking in this area here for the 100 radians per second, we see that the first order system has a magnitude of negative 10.5, exactly as we saw in our first example, whereas in our third order system, the magnitude drops to negative 32.3 decibels. We want to convert this back into the linear, so I want to raise 10 to the negative 32.3 over 20. So we're going to see it's about 2.5% is what's going to be left of that original amplitude. And once again, if we compare that to a first order filter at negative 10.5, there we're left with about 30%. So we're going to see much harsher attenuation of those high frequency signals in the third order versus the first and even the second. All right, so let's just run everything and see what the simulation looks like. So here we see everything laid on top of each other. Once again, blue is our unfiltered signal at those two frequencies, the 1/2 radian per second and the 100 radian per second. Red is our first order that we saw in our first example. And now we have our second and third orders as well. It's a little bit tough to see the third order as it's going to look pretty similar to the second order. So I can zoom in a little bit so we can see some of the differences. So if we zoom in, it's maybe a little bit easier to see, but we see that the low frequency oscillations were really not affected in any of the first, second, third order, any of the filters that we used. It's that high frequency that we are going to be noticing this attenuation. So certainly the green, the second order, is easier to see. We can see its amplitude of the high frequency wave is smaller than the first order, which is again smaller than our original. And the cyan, zooming in maybe even a little bit further, we can see that that has an even smaller amplitude at the high frequency than the second order does. But also if you notice what's happening, our unfiltered blue, that peak is happening before our first order because of that phase lag, which happens before the second order, which happens before the third order. So the time is getting delayed further and further as we increase the order of our filter. So we got some benefit that we got smaller and smaller amplitudes of the signal we wanted to remove, but on the downside, we are lagging further and further behind our input signal. So it's a trade-off when we're using these passive filters and we're increasing the order, what's going to happen. So as I discussed before, how can we make a second, a third order passive system? Well, one way would be to be cascading these first order filters. We use the output of our first filter as the input in our second, the output of that as the input into our third, and however many layers we want to achieve the order system that we want. And we see here they're simply put together as just a resistor and capacitor, and we can not only increase the order of our low pass or high pass filter, but as I said before, we could construct band pass filters by putting a low pass and a high pass in this cascading fashion. But again, we get this trade-off between phase and magnitude. One thing we can do instead of using these passive filters to combat this trade-off is to use an active filter. An active filter uses op-amps and different types of construction to improve that roll-off, but also reduce the lag that we're introducing into our signal depending on their construction. So one active filter that's common is the Butterworth filter, and we can have different orders of Butterworth filter as well. We can have first or second or however many, and that too is going to affect the roll-off. And generally what we can see is a better phase diagram or a more attractive phase diagram that we're going to have in the Bode plot when we compare it to these passive filters. But on the downside, they might be a little bit more complicated to construct, might take more elements, and also active, as the name implies. The active comes from needing external power for these op amps to function.